Hello, Year 10. So today's task is going to be the linking learning and the homework task. So I'm going to explain what you have to do, and then I'm going to walk you through it. So here's the linking learning. These tasks, which you've seen before, remember they link stuff you've done a long time ago to what you're doing now, to linking them all together to make a difficult question. So here you go. I need you to go through this task and answer each question. You can do it in the box if you want to, or you can write it on a different piece of paper. So the question is, explain how Hooke's law can be used to find out the spring constant of a spring. That's what you did last key stage. So last week, which is not quite last week, seeing as everything's been a bit messed up with the home learning. So draw the magnetic field around a solenoid. Last lesson, describe how an electromagnet can be made to have a larger magnetic force. And then linking this all together using this diagram, describe how a student could use this apparatus to investigate how the size of the current affects the strength of the electromagnet. Okay, once you've answered these three questions, you should be able to link all of that learning together and answer the next one. Then, what I need you to do so here is the homework. And we've done circuit breakers before, but again we're revisiting it now because it is linked to magnetism probably just as much as it's linked to electricity. So a 6 marker describing in as much detail as you can how this circuit breaker works. Now on the right hand side of the page you can see the mark scheme. So what I'd like you to do is try and answer it first, and I'll give you an extra space so it's harder to see when you're doing it. So try and answer this question first, switch over to like green pen and mark it afterwards. So they're the instructions. Now what I'm going to do is I would like you to pause this video or go away from this video and have a go at these tasks. And what I'm going to do is in 10 seconds I'm going to start going through the tasks and giving you the answers. So I'm just going to sit here awkwardly for 10 seconds. So hopefully you've had a chance to pause the video, do the task and come back to it. We will start with the linking learning first. So I'll get my pen. Okay, explain how Hooke's law can be used to find out the spring constant of a spring. First of all, because my handwriting is horrible and I've not got a lot of space, I'm just going to write all over the box. So I'm going to write a little arrow here. We know that Hooke's law is the force on a spring, or the force exerted by a spring, is equal to the spring constant times by the extension of the spring. So how can you use Hooke's law to find the spring constant? Well, first of all you need to have the equation rearranged, so it would have to be K equals F over E. There's your equation that you need. Now what would you do? You've done this experiment. You need to attach spring to clamp stand, much like this diagram here. You've got a spring suspended from something, okay, and you place different masses on the spring, and then you measure the extension. So attach the spring to a clamp stand, you place different masses on the spring, you measure the extension. This is as simply as I can put the experiment. You remember doing this. You got your spring, you hung it from something, you measured the length of it, you put a mass on, you measured the length, you put another mass on, you measured the you kept doing that. And eventually you converted the mass to weight. Okay, so that would be a force. So this mass was then converted to a force, because remember, it was about 100 grams ish equals 1 newton. Then you converted the length to extension, so how far did the spring stretch? You then plotted a graph. Okay, so then you had force, extension, and the gradient of this graph gave you the spring constant. So there's the spring constant. Last week, draw the magnetic field around a solenoid. So this one's a bit easier. So I'm going to draw my solenoid. There it is. So, can I change the color of my pen? I'm not sure if I can. I won't try and do that. Solenoid is just like a Barnett magnet. So there we go. Get my field lines like this. One going straight out, straight in. Field lines on the outside. They get bigger as you go further away. If my diagram's a bit rubbish, just Google magnetic field lines around the solenoid. But that is what it looks like, and the field lines do carry straight through. The magnetic field is the strongest inside the solenoid, and that's why we put a iron core in the center, because then that amplifies that magnetic field and projects it round. Describe how an electromagnet can be made to have a larger magnetic force. Well, first of all, add, which I just mentioned, a softer iron core. Second one, add more. Remember, this is saying how to have a larger magnetic force, so you have to state what specifically do you have to do to make the magnetic force larger. You can't just say change the number of turns on the coil. You have to say specifically there is more. So there are more turns of wire on coil. Now that language is very important. You have to say turns of wire, but I've already gone over that. So let's see. And then the last one is you would need to have a larger current flowing through the coil. Now, hopefully we all were able to get those three. Again, I'm going to pause for 10 seconds so that if you were stuck on this one, you can pause this video and have another go at it. Okay, because this is all the information that you need is here to be able to answer this one. So I'm just going to wait a little bit. Okay, let's continue. So describe how the student could use this apparatus to investigate how the size of the current affects the strength of the electromagnet. So, first of all, you would have to, you'd have to calibrate this spring. And the way you'd calibrate the spring is by doing this experiment, because you need to figure out the spring constant. So, I'm just going to say, to start off, we're going to do experiment 1, and this will calculate the K. Okay, so you know the spring constant, you know how far this object will extend compared to how much force is applied, and this is calibration. Because having a spring, if you stretch it, you don't know the force, but after you've done this experiment here, you will know exactly how many centimeters has gone down, and you'll be able to convert that directly to a force. So this is for calibration. Okay. Once you've done that, you're going to have to hang the iron nail on. So attach the iron nail, and then you're going to have to set a certain point to being 0, because the iron nail is, even though it's a small mass, it is a mass. So you attach your iron nail. So like this magnet's on, so that's why it's being pulled down. So let's just say my spring, then I had my iron nail. I would put my ruler so that 0 was at the correct height. So you see there's a little measurer there. So I'd have my measurer at 0 with the iron nail on and the magnet off. Attach iron nail and set to 0. Now, Next bit that you have to do, well, you've got to, because it's saying how the size of the current affects, you'll need an ammeter. So you're going to have to measure current using an ammeter. Now that's very important, even though it's obvious to you. The examiner does not know that you understand how to use an ammeter or what it's for, so you have to say it. Measure the current using an ammeter. Then you would conduct this experiment for different values of current flowing through that solenoid, and you would be able to convert the movement of the iron nail, or the extension, I should say, of that spring to a force, which would then you'd be able to plot a graph. So I'm going to say collect range of results for current, and that's what you're changing. You're changing the current through that coil. Then you're going to plot the graph, right? And you're going to plot a graph of current against force, because you're changing the current. So the x-axis is going to be the current, then the y-axis is going to be the force, and there's your experiment. Hopefully you would get a graph that would be a straight line like that, because you know, using this equation, you know, if you ignore everything and just look at force, and F would be proportional to current with some, and then with, yeah, so you ignore B and L. As long as you keep everything else the same, F is proportional to current. So that would be the linking learning task done. Now, discard the ink, get rid of that. So let's have a look at the key homework. Circuit breakers help make electricity safer. Describe in as much detail how this circuit breaker works. Okay, normal use. We'll start with red pen. So normal use. There would be a current. There would be a current flowing through the electromagnet. This current, so specifically this current is not large enough to trigger the, I'm going to call it a circuit breaker. So this current is not large enough to trigger the circuit breaker. Now, let's go back to our red pen. So normally we know that there is a current flowing through the electromagnet. The current is not large enough to trigger it, because during normal use there will be a magnetic field. It's just this spring is stronger. So if current increases, well, what happens? If the current increases, then the current through the electromagnet increases too. If that happens, you've got a larger current flowing through the electromagnet, so the magnetic mag field around, so I'm going to produced, that's a D, produced by the electromagnet increases in strength. Okay, so now what's happened is here, this electromagnet is now stronger. Okay, so if that electromagnet is stronger, this iron bolt, which is an induced magnet, will be attracted to the electromagnet with a greater force. So, iron bolt becomes a induced magnet. It's attracted. Actually, that's a separate point. It becomes an induced magnet and is attracted to the electromagnet. Right, because the force is now larger, we've said before, this increases in strength. Because of that, the iron bolt moves left. Or you could say the iron bolt moves towards the electromagnet. This causes the plastic plunger to go up. If you look at the top here, the iron bolt, is this bit here is the only thing stopping that plastic plunger from moving, and if that is moved to the left, there's no longer something blocking it, so this plastic plunger can then move upwards. So plastic plunger moves up. After the plastic plunger's moved up, notice that this is where the plastic plunger is touching the circuit, and here, this is after it has been reset. So this is after it has been triggered. So notice the circuit is broken, so you have to say circuit is broken, hence the name circuit breaker. The last point, you would say to reset, you would press the plastic plunger down. Plunger down. Okay. There's both of the answers. Please mark them, see how well you did, and then email it back to me.